All right, welcome again to another episode. In this one, we'll be doing binary search tree data structure, like the BST. So in this one, we'll be like more focused on theory, not more focused on 50-50. We're gonna do both theories and practical, but more inclined towards practical. 60% or maybe 70% is practical, 30% is just theoreticals. So I have okay, let's just jump into the theoreticals. So what exactly is binary search tree? Binary search tree is a specialized type of binary tree where each node has its own key. It maintains a specific property. For any node, all keys in the left subtree are smaller. All keys in the right subtree are larger than the key of the node itself. This property makes searching, insertion, and deletion efficient in BST with average time complexity of 0 log n. For these operations, tree is really balanced. I'm assuming that this does not require any kind of specific detailed explanation because this is written in basic English and basic simple terms. So let's look at the properties of a binary search tree. The most common thing first, node. Each element is a is in the binary search tree is called node, which contains a key and a possible pointer to its left and right child. Then there is the root, the topmost element of the binary search tree. Then there is loop, then there is leaf, a node which has no children at the end. The node which is at the end, which does not have any children whatsoever. Then there is the height. Height is basically the number of edges, or let's just say edges on the longest path from the root to the leaf. Then there is depth. The distance from the root to the node is the depth. So these are some properties that are usually used in binary search tree whenever you tries to denote it, whenever you try to denote some kind of like basic situation, or whenever you are trying to explain everything. These are the terms that you have to use. You cannot just simply say that this is the dot or the dot in the middle or something like that. You have to use these kind of um, properties, so let's just say words, to explain binary search tree. Then what are the things that we're going to do? What are the basic operations that we're going to perform? Insert, search, delete, and traverse. Insert, add a new node to the binary search tree. Then there is search to find the given node with the key. And then there is remove a node, and then visit all nodes at in the BST in specific order. In three different orders, we're going to do that: in order, pre-order, and post order. These are the things, and at the end, level order, obviously, as we do in every single data structure. So this was pretty basic about the theories. Now let's just jump onto the practical and see how exactly it is coded. And I'm gonna give you like the steps along the way so that you can understand it pretty quickly. So let's just start with the insertion operation. No, first we'll create the node and the binary search tree. Right. So as always, we are onto our screen. Now we can start coding class node. Inside of the node, we'll initialize it. Dot left is equal to none, and self right also none, because starting node does not have anything. In your beginning, when you're starting out with your first node, like the first ever element, which is going to be your root element at the end, it does not have anything in its value. It does not have any children. It does not have its own values, nothing whatsoever. So now let's just start our binary search tree. First thing in it, then self dot root, and now let's just do our insertion operation. So let's just do our insert operation. So all you have to do is just define insert, then self comma key. If self dot root is none, then self dot root is this, and that's it. So how do you exactly do the insertions? First thing, it's basically divided into four different steps. All right. Start at the root, compare the key of the node with the current keys node. right? Then if the new key is smaller, move to the left child. If larger, move to the right child. And then repeat the steps 2 or 3 until finding a none position where a new node can be inserted, right? You have to just find a position where it is like basically empty if it does not fit anywhere. It does not have any kind of like rocket science inside of it. So I'm basically using the underscore insert, and underscore insert has all the logic because I don't want it to like our insert function to go too long. So I'm dividing all of the functions into two different, let's just say, functions. Any method that I'm dividing, every single method I'm dividing into two different functions. Even the search, even the delete, every single thing will be divided into two, so that we can have like good code management. Definition will be on one, and then there will be another one into like the management and stuff where the functions are being performed, where from which function you can call. So you can call the insert one, and insert will call the underscore insert one, and underscore insert will execute all of the things and give it to insert, and insert will give it to us. So this is basically simple. This makes the code look simple and prettier, and also readable enough to understand what exactly went wrong if in case it went wrong. Then there is the search. Search is basically simple. You just have to go through the stuff. Search basically does not have too much of it, but all you have to understand is start at the root, compare the key to be searched with the current node's key. If the key matches, then return true. If the key is smaller, search the left subtree. Go on to the left side if the key is smaller. And if the key is larger, go on to the right side, right? Because that is what we have discussed. The smaller things are on the left side, the smaller element or the small node is on the left side, and the large node is on the right side. So that you have to understand that if you think that the value is smaller, go on the left side, larger, right side, and repeat this step 2 or 4 times until the key is found, or the subtree is empty, or maybe none. See? If key is larger than node, if node.key is bigger, then go on to this side, and if not, then go on this side, right? Now it's time for delete operations. So delete, define, delete. Delete is also been divided into two different parts: delete and underscore delete. That's it. Simple as that. I'm not making things too complicated, so that's why I'm doing this. So delete also have like 4 or 5 steps. So the steps are pretty clear. Start at the root as always. Then find the node to be deleted using similar approach to the search operations. As we are using in the search operation, we are doing the exact same thing. But if the node has no children, simply remove it. Simply remove it. If the node has one children, replace it with its child. And at the end, if the node has two children, find its in order successor, like the smallest node in the right subtree. Copy the in order successor key to the node and delete the in order successor. You have to copy the key and then delete the node. So let me just show you in the practicals. It might be more clear to you if you see it instead of just listening to it, right? And just because we need like the small successor, we have to have like an min value node. We'll require that. Why do we exactly even need a min value node? I'm going to define a min value node because let's just say that, let's just say in a simple hypothetical sense that you have a node with two children and you have to get the in order successor. How do you exactly do that? You need to have the minimum value node. Like you need to find out the successor, right? You don't need the predecessor, the successor. To so to get not to so to get the successor, you have to find the minimum value of the minimum value node. How do you exactly find the minimum value? Current is equal to node while current dot left is not none. Current is equal to current dot left and return current. That's it. You found out the current, delete the current. That's it. Turn the node. All right. Now define the underscore main underscore value underscore node. All right. So it's going pretty decent. Self comma node current is equal to node while current dot left. So current is equal to node. Perfect. And prepare underscore. Then while current is equal to current dot left. Return current. Ah, boy, it was perfect. Welcome to Traverse Operations now. Let's just do the four going to be like four different traversal operations in order, pre-order, post-order, and level order, right? So in order, basically left, root, right, pre-order, root, left, right, post-order, left, right, root, and level order, top to bottom, left to right. Not specific to binary search tree properties. It is just as that level order is simply top to bottom, left to right. That's it. So in order, this has like basically simple, exactly the same code. Like not exactly the same code, but most of the same code. It does not have too much complexity in it. You just have to define it in the manner. Self dot in order, node dot right. Okay. Then pre-order self dot self comma node. And then if node is there, which obviously is going to be if we have inserted any kind of values inside of it. And if there is, just copy these things here. Just copy this thing, paste it, just make it pre-order and change it to left, alt shift down, make it right. That's it. We're done with pre-order. Now define post order self comma node, and then if node is there, then copy this entire thing, paste it, just make it okay, tab, perfect. Just pull it down. All right, now post order, that's it. That's it, perfect. Now we're on to our last order, which is level order. So level order is pretty simple, not too complicated as an order. Mm, Return, then q is equal to self root, and while q node is equal to q dot pop zeroth element, the first element. All right, then print the node dot key. If node dot left, q dot append node dot left. And if node dot right, then q dot append node dot right. That's it. Then we're going to define, create an object and start the implementations and see what we get as an output of this one. So we're going to do a bunch of insertions, then we're going to do in order, pre-order, post order, and all of those things. Okay. Perfect. In order, then just say print. And the exact same thing will be going on for next all orders. So we're going to just copy paste it. Post order, level order. Then what I have to do is just simply say delete or maybe search. Let's just do search first. Search 50 and then you have to do delete. Okay, guess it's done. Just run this. For that, let's just say after deletion, print any like order. Let's just say in order, for example. And then say print so it leaves a space. Do this for 3 others and that's it. And we have an error and that says in 118th line. So this is the error. So level order has the error. So let's just go on to the function level order and just try to find out. And we forgot the indentations. The if part was supposed to be in while. Till it's inside of it. Let me think about it. Okay, let's just run this again and see. Save and run again. Okay, node dot key. It was supposed to be node dot key. Yep. I guess now it's solved. Maybe. Still, I don't know. Maybe okay. I don't know. Let's just try this again once again. Maybe I didn't save it or something. Okay, anyways, the code is finally all completed. You can find this entire source code on GitHub. So see you in the next one with some new long